Okay, so I'm going to start by reminding you quickly what we were doing the previous time. Every now and then, I guess I will have to accept some new attendees. So please, what I told you before I started recording, please, like help me to add them, like send them the links, let everybody the calendar link. Just invite them like to the calendar, and then they will be able to get automatic admittance, and I will not have to deal with it. Okay. And what we did last time, and now I'm doing it on another computer, so it's going to be a little bit different than the recording, is that we actually we talked about how to build a kernel. And I gave you like the GitHub repository to do everything like in an automated way. And we used some configuration file, and then we just built the kernel. And on top of it, we built a minimal RAM disk that was built based on BusyBox. So I am going to talk now about the things that happen way before the RAM disk gets into action. And perhaps either this time or the next time, I will continue the discussion of what's going on userspace. Okay. So the target for that is going to be on QEMU. And the other thing that we did actually was talking about the boot, process in a very shallow way. We talked about kernel versions and how to get a kernel. And we talked about something that is very important. And in this particular, like in the last embedded Israel meetup, I did not give it too much attention. I gave it a little bit more attention on Fosnor's talk. That, as I mentioned, many times I talk about the same subject, but from different perspectives, or like maybe the beginning of the talk will be identical, and then the second half will be completely different. Okay. So what I did talk about back then is a little bit more about like video modes and things like that. So these are things that are very, very, very much dependent not only on the emulator on QEMU, but also on the hardware that it provides. So what we're going to do now, like in the next hour or so, is actually minimize the dependency on it by concentrating on the boot process of x86. I will also mention what is going on in ARM. And the most important thing that I hope you will get from this talk or from this series of talk is that you will be able to go ahead, reproduce the steps, explore yourself, and maybe give a talk yourself in the next session, in the other session on a particular area that seems to interest you. Okay? So it's going to be a little bit less organized, but we have a lot of time, so it's pretty good. Okay? So speaking of what we did, we ran with QEMU, and I told you that I prepared a very, very, very minimal configuration that only enables like a serial in terms of I/O and VGA console and physical keyboard. Again, on QEMU, so as physical as it can get. And I told you about some configurations that are very, very important. Okay, so just take a couple of seconds to look at this particular slide. So it says display output, keyboard input. And we have here VGA-con, which is a console, VSFB, which is a frame buffer. I'm very happy to elaborate on everything, okay? So, you can write, you can jump brutally and interfere, but we're not going to elaborate on this right now. And there are the next two lines that says rely on BIOS. Now, on the x86 world, BIOS is something that is like really, really, really great for bring up. Why? Because you can use a lot of existing operations that the BIOS actually implement for you and rely on them if you know their API. For example, if you know that if you want to output something to the display, then the API would be the gate, the interrupt, x10, okay? So if you know the API, you can get all kind of activities from the BIOS themselves. Let's see who tried to join. Didn't do anything. Huh? Okay. All right. Yeah, so sorry. So, and let's have a look. Yeah. So you can get a lot of services, like just by not doing like anything, okay? So when we talk about like the hardware that is provided to us and the BIOS that is provided to us in QEMU, then you don't need to even do anything. You get to see BIOS, Open BIOS for free, okay? So when we have keyboard services, display services, and the like, we're just going to use that. Having said that, the operating system that we are going to be developing right now, for which, and now let's get back to things that we did show earlier. Let's go like to the Linux tree, okay? I told you that under init main.c, by the way, if there are joining requests and not chat requests while I'm talking, please feel free to, to redirect my attention so that I will move back to the Meet window and I will approve them, okay? A DisplayPort cable that I had got destroyed and I have only one screen now, okay? So I will simply not see them. So I will ignore like any other noises, okay? So in the previous time, we reasoned this. We have this nice file in the kernel source tree that is init main.c. And I told you that the general purpose architecture independent entry point is a function which is called start kernel that looks like this. This is a hint for external linkage, okay? It's called start kernel. And this nice guy here, underscore underscore init, means that once this function is done running, and there is something very important about it. It's not exactly that this particular function stops running, because it's going to do quite a lot of things. And at the end of it, it's going to move control to arc call rest init that will in turn move control to another function called rest init. So once this entire cycle is done, and I did mention a couple of things that happen here, and I can talk more about it, in another session, of course. Then look what's happening. So check out arc call rest init, okay? So arc call rest init, every time you have arc, pretty much means that it's going to be something architecture specific. Let's see if it appears in this file. So arc call rest init, look what it says here. We have here an alias weak that depending on the architecture, then either the rest init function will be called directly here, or perhaps I compiled it in some any other way, and another function call will be called. But the important thing is that this is a direct call to this function that calls directly this function, rest init, where we mentioned two very important things. Kernel init, that's the first PID, right? Like if you go and do like px and you see PID number 1, then this is this kernel thread that later is exec and becomes the first user space process, all right? And it also starts another thread called kthread-d, and actually went lost here. Where is rest init? Yeah. So the other thread, kernel thread here, and I did talk about it like the previous time, it's just been almost a month, is going to be this guy. And I told you one important thing. I told you, hey, there is something that like this underscore underscore init that we're going to do something with it. And this something is going to be completely discarding all the memory that it uses. So this is going to be done in this first thread called kernel init. This is completely architecture independent, okay? And one of the things that it's going to do is going to call free init mem. For the security people, it's going to also call mark read only and so on. But at the end of this process, and this is going to actually be a process, we're going to do exec ve to a file that is on a file system. And those who are interested about what file systems are, then I can teach about it like in some other time, okay? So that's like what we do. We execute, and then we have the user space processes, right? For which, and this is a little bit of a different version of what I showed last week. Maybe I will log in from another computer and show it. Just to remind you, we had all kind of like setup scripts, okay? And we're going to start by env setup. that does all kind of things. In this particular case, I set the architecture to be i386, and I have these folders, and I already built the kernel. So the kernel will be in kernel out, which is this guy. And I have all kind of scripts, for example, run kvm, that is going to be running Linux distro for me, okay? Now, here I used another branch in my Git repository, tinyconfig, whereas in the previous session, I used the FOSS 2020, which was much more elaborate. But the important thing here is that I have user space, okay? And this talk from this moment on will not address this anymore, all right? So back to our init code. So we mentioned that we have kernel init, which is responsible of actually going ahead and starting the first user space process. But how did we get here? So how did we get here? We had the kernel thread, right? That was called by rest init. I deliberately say the same things over and over and over again, all right? And that was called by arc call rest init, right? And here we have all kind of things that should be very interesting for us. Speaking of hardware-dependent mechanisms that will necessarily be prefixed with arc. Actually, a CPI, which is for like resource discovery, like you don't really need it if you have like a device tree in ARM. And like always, device tree, we'll talk about it some other time. Every time I don't mention something, it's an opportunity for you to offer a talk in our next meetup about it. Because otherwise, sooner or later, I will give a talk about it, but I want to give everybody the chance to do it, right? So we have a lot of architecture-dependent stuff, okay? We have also subsystem dependent stuff like, okay, we want to initialize credentials. Credentials, for example, if you want to know how user and group work like in Linux, it has to do with its struct cred that takes care of it. Security has to take care with the Linux security modules like AppArm or like SE Linux and the like. C group, all these are all kind of subsystems. Do not confuse them with another type of subsystem, which is known for like device drivers, which I'm going to talk about later, okay? But we have a lot of initializations, but we have a lot of hardware-specific stuff, architecture-specific stuff, that we know for sure they're architecture-specific stuff because they have the arc line before that. So let's just search for the word arc in a very naive way. So we have here init call level names when we talk about the order in which we initialize things, or if we talk, then we're going to see what is the order of them. But you can pretty much assume, trivial logic that says, okay, we have an array here, it has level, then there are all kind of names, for example, late or poor or core, then probably this has something to do with the order of where functions are going to be called. And if you bother to look at do init level and the likes, then you will see that this is how it is. This is the topic for another talk, not this one. So the context, we're searching for arc. So I'm just searching for arc and searching for arc. And here we see this post ACPI subsys, and we see this rest init, and we see setup arc. Now, where do we see this setup arc and what is going on here? So the function, as I said, 100 times, I think, is start kernel. Now let's see the beginning of it, okay? So we have here task stack and magic, never mind where it is, processor ID to set up. So if you want to see like what SMP processor you're in and so on, debug object early init, we can go to this and to C group maybe later. Local RQ disable, don't get all kind of interrupts on this particular CPU. If you develop device driver, if you develop all kind of like core kernel code, then you will need to know quite a lot about what is preemption disabling, what is interrupt masking, what is interrupt disabling, and so on. But this is not the subject here. Here we take care of a subsystem of the boot CPU, that is where this function is actually running, okay? About pages. And here is the Linux banner that you know. Like when we run a Linux system, then we're going to have this thing. Linux version, yada, 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 and so on. Okay? So let's see if it's a question or somebody joined. Every now and then I'll look at the chat. All right. Okay, so where were we? So the banner is something that is going to be printed out relatively late in the initialization process of the kernel. It's going to be completely architecture independent, okay? And this nice line here is what takes care of it. So PR notice means that this essentially translates. I'm saying it like slowly, even though it's trivial for those who never did really any kernel development. This is essentially print K that I assume that everybody heard of it one time or another with the priority of notice, okay? So for those who don't know what print K is, then it's a facility that the kernel implements to provide you the printf-like functionalities in all kinds of ways. And like always, you already know. Maybe we'll talk about it some other time. But we have here early security init for the LSMs, and here we have something super important. Setup arc that receives the command line, okay? So let's see. I'm going to get back to it because it's super important, but let's see like what other architecture specific things we may have, okay? So of course, in all of these functions, there may be call to architecture specific call. But if we look now at the function that I say is super important, that is setup arc, this guy here, then you will soon enough see that it's going to be under the arc directory that has for each architecture specific code, okay? So the architecture that will interest us today would be ARM and x86. We'll start with x86. The reason for it is that, as I mentioned before, we have the gift of BIOS implementation that help us do all kinds of things, okay? So let's take a step back and I will show something, okay? So let's see what is our kernel out. And I added some things here, okay? So you will see additional prints. This is for our discussion. You can ignore them. I'm just going to talk about several particular things. So this is the kernel out that I'm going to run. And our run KVM script that we had before looks like this, okay? So what I'm going to do here is get rid completely of the kernel parameters, okay? I will get rid of the no graphic ones. So I will let like the default display of whatever QEMU provides me be whatever that runs, okay? I will also get rid of the initrd, and I will also get rid of the kernel. So I will run nothing, okay? So when I do this, look what's happening. I mean, I have all kinds of prints here, right? And it's going to start to do netboot, and it's going to start try to do booting from ROM and booting from DVD and CD and all these kind of things. These are things that QEMU implements for me, okay? Now, when I give QEMU, and of course I can install here grub or something like this, but I will not do it. But when I give QEMU the kernel parameter, I didn't mean to do that. Let's get rid of like the console and things like that. I don't care about it now. I'll get rid of no graphic and also get rid of like the initrd here, okay? When I give it this, then it's going to start and run all kind of things. Here we didn't give initrd, so we have a kernel panic, right? If I now go one step back and I provide it with the append, let's say VGA equals ask dash append, then look what's going on here. Like cBIOS, that is the BIOS that I have, booting from ROM, and then look at this message. This was supposed to be a color, but the terminal doesn't interpret colors, so it's okay. Welcome to ROM's demonstration. Boot header S says I. Run 0, print k run 0, something that looks like address. Press enter to see video modes available. Continue or wait 30 seconds. Let's see the video modes available. So here, because I didn't configure VESA and because I didn't configure a lot of things, then as opposed to our previous talk, then we don't have all kind of nice and shiny displays. But what I can do is like choose one of like the modes that will look nice. And yes, we have VESA modes, but they're ridiculous. I mean, they will not support high resolution or anything like that. So let's go ahead. I'm going to select one of them and I'm going to boot. And this is like what I have, okay? I have like, hey, kernel that is running. If you're not convinced, then I am going to go and run it like with the RAM disk. We'll get to a prompt and we'll all be happy, okay? By the way, are there any questions or comments? Because questions and comments, please, jump in. I just want to make sure that nobody's like bored, because as I promised, this is going to be a dynamic agenda. And as you can probably understand, just to show a simple concept, I can spend, 1 week, 24/7, to actually drill down and say the things. So I'm saying things like I give a taste of some things that are around, but we do have particular focus. I just want to make sure that you're with me. And also, it's very important, to try not to make this talk way too long, because it can be boring sometimes, right? So let's do that, okay? So I'm going to go ahead and run what I ran before, okay? So I'm going to be a little lazy here, and I'm going to append. I will not lie, I'll do exactly like before. So we'll have the stop, VGA equal that. Then I will explain you also what it does and how it does. And we'll do enable KVM, because apparently it's not
You need
that
the dash
default. Huh? Yeah,
on the append.
that's true. My favorite mistake. So we have this thing, and then we'll have a boot. I'll select something. I could, doesn't really matter what I select. And then I have like my terminal, right? So that's what I have. And here we can see that the init script that I had is not exactly what I had in our final and better version of our mini Linux distro that has like this nice banner of the PSCG and so on and so forth. But we have init. We are convinced and we're happy, okay? We have a system that is working. We have a mount points that are mount like proc, sys, and so on. Now, before I actually go and show you the super, super important thing that I promised, that is set up arc, let's have a quick look at what we have here. By the way, we also proved that we can work also like with a display and a keyboard, that is this one with a QEMU window, or with serial, which is what I ran when I did the no graphic parameter. So since I mounted sys, and this was actually going to be the original topic of the meetup, explaining about unified device model, or like how I actually managed to populate dev.
Ron, you have 2 questions waiting in the...
All right, I'll get back to it in a second, okay? Thanks, Eyal.
Okay, sorry.
No, don't be sorry. Thank you. So one of the things was like how I even managed to populate this guy. So the answer to it in the init file that I presented to you would be doing something like using mdev. So if I use mdev from BusyBox, then automatically then it will all be like nice and colored and stuff like that. By the way, check out the colors. The reason for the color are the display mode. If I run it in another display mode or ever like serial, then I will see colors, not just monochromatic. Okay. So back to sys, we can see that we have much, much, much less directories everywhere. This is just the top 3. Then if you go ahead and look at sys in your own machine. So let me just do it quickly. So we can see that we have some sort of minimization, right? We have less thing. Now, I'm not going to get into it too much, but I did this mdev that figured out all kind of things, and it figured them out because it knows the dev. And it also knows that, sorry, because it knows sysdev. Okay, block and char. So under char are millions of like parameters that were automatically populated. Okay, so sysdev char. Yeah. But the important thing about this guy would actually be understanding how the device tree model works in Linux. So this will be a topic for another time. I just wanted to prove that this particular init also took care of like automatically populating the device, the dev/dev directory. And just for the curious reader, we can see that there are classes and buses, which one can argue that class or bus should be called like subsystems. And just have a look. I will not talk about it right now. But just know that we have like writing ability because we have like TTY here, and we have particular devices. That is what is important. Here. So I don't really have any interesting device here except for under platform, where I have keyboard and a serial and a platform frame buffer. If you look at a device like this in your machines, you will most definitely see PCI. Okay, so like if I look at like a sys bus, then we have SCSI, we have PCI, we have PCI Express, and if we look at the devices, then we'll see all kind of like things here. Okay, that some of them are like they're categorized under some things, and this is not the topic of this particular conversation. So we have the minimal system here with very minimalistic hardware, which is of course hardware specific. What we're going to tackle now, as I said and promised and will do, is architecture specific code. So just reminder before I look at the question, okay? Like if we look at init main.c, we look to start kernel, which is called externally. And today we're going to figure out from where, okay? And somehow we have function data set that is super important, that is called setup arc, that receives a command line, okay? That presumably is somewhere in the memory. That we're going to call. But I mentioned that this code is completely not architecture dependent. So we're going to have two objectives here, okay? Figure out who calls start kernel and see what this setup arc here, okay? So if I want to play it stupid, I'm going to go to the architecture specific code. And let's say that I look over all architectures, okay? And I'm going to look who calls start kernel. And we will see that not too many files call start kernel, but we will see that many times there are, this is like arc, J is a branch over there. This is arm, B is a branch, jump over here, okay? Every time, just have a look. I'm not going to go one by one. We'll see that something like the word head appears. And it's going to be written in assembly.s. So let's have a look here. And if I go and look in x86, I will also see that we have here a function that calls start kernel. Now it's a C file, but it's still architecture dependent. And we're going to have also for 64. So we are getting pretty much convinced, at least I'm pretty much convinced, that start kernel is being called from architecture dependent code, all right? Now, so some architecture dependent code calls the start kernel that is architecture independent. And this guy, in terms, calls setup arc. So here we have a couple of more candidates. Okay. And so the reason for this is because we have all kind of function pointers that set up the pointer to the specific machine that does it. Excuse me 1 second. Okay, so whenever we have like platforms where you can use like the same processor in many different variations, then you're going to have machine-specific code that may do other things for the setup arc. So in x86, the good news is that we don't have this, okay? So look what we have here. So if we look like at the x86, we're going to see all kind of comments. This is not what is interesting for us, okay? We're going to see, hey, like called from this, called from there, all right? And apparently, we're going to go and if we see like in ARM, the code, and we're going to search for arc ARM. So we're going to have like all kinds of references to it, okay? So for example, we see here in setup.c underscore init setup arc, okay? It receives a command line, just like we saw. In ARM64, we also see that. And we see once again the prefix init. We'll see it also in the x86. I'm sorry if I'm going like too fast or something like this. So this is in the x86, okay? And we can get like the feeling that code looks more or less the same here. So let's see what this setup arc does. So this is init, which means that after rest init is called and the init first process, speed1, is called, we're going to actually clean up the memory of this, okay? So I will start with x86 and just show you like how start kernel is called and how setup arc is called. And let me have a look at the chat. So yeah, so kernel panic happens. I mentioned it the previous time.
Could you make the text a little bit bigger around?
Excuse me?
Could you make the text a little bit bigger?
Yeah, I can and I will. Yeah. So, okay, I see two questions about the kernel panic. It happens with a direct call to panic if there is no if there is no init or initial root file system. I can explain it later, okay? It was like a little bit of the topic of like the first talk, okay? So I will, you know what, speaking like 3 words about it, then if we go to init main.c and we fail to try to run init process, we fail several times here to find a root file system or to find like the file on the root file system, then we're going to panic. Like that's it, okay? So this is like the short answer for that. Now, Eyal, let's see. Let's assume we run without init RD. It's the same question. Is it still possible to, yeah. Okay, yeah. So it's super possible, and I'm going to talk about it. Like the idea is that, and I actually talked about it the previous time also, when I discussed this user, there is like the user folder under what's its face? It's under the kernel actually. So there is like the script here that tells you, hey, where do you want to actually go ahead and take care of it or like generate it? So we have like the init ramfs data friend here that is going to include binary. So this is how you go and put like the RAM disk, boom, inside of the kernel. Now, when we look at ARM, we will see that actually I'm very tempted to show it right now. So I will show it in a millisecond or two, but will not explain too much. Like in the ARM boot code, compress something like, yeah, in boot P, there is like the boot protocol. Then we are also going to have like the init RD included, okay, inc bin. And then essentially what we have here is like a way for, we have a loader script that says like where we start things, and this is the entry. We'll talk about it later, okay? And we're actually going to go, and if there are the corresponding files, we're going to concatenate them. So I'm not going to talk about it too much now, even though they are pretty, small, but we include the init RAM disk in ARM, just like we include like something called the Z image. I'll talk about it later. And we like put them in the binary that like you flash, that you boot, that you separate, that you reverse engineer, like as per the question you asked like in the forum some other time, and so on. So if you want to see like some of the things that like happen, like you would want to go and look at this makefile, mostly on makefiles that are like on upper levels. Okay, so those are some things that could and should interest you. Okay, now back to our topic. So I said, all right, I said that now I'm going to concentrate on x86 for the sake of discussion. So we reasoned that we have under kernel setup.c that as the setup arc. The setup arc command, okay? So I'm not going to dissect it. If there are requests, I will do it later. But I just want you to know it that we actually go ahead and call this code in an advanced phase where we actually already have like the Linux platform independent code running. So we can see that we are going to take care, for example, we already have paging enabled, for example, in this case. We're going to go ahead and take care, for example, of description tables and things like that, and take care of things that are very, very, very x86 architecture dependent. And we'll have it also like in ARM also. So we're going to see that there is the command line here. And the command line is actually going to be affecting things both in the architecture dependent code and in the non-architecture dependent code. One of the things it can affect is the level of verbosity much before you have the print K subsystem in the Linux kernel, which is super important if you want to go ahead and do, a bring up and debug what you do. So I warned you ahead of time that this could turn out to be very, very, very long. This is why I'm not bothering to actually talk about, a lot of things. But some of the important thing is that if you want to do device enumeration, you need to understand ACPI in x86, or you need to understand device tree. So this is being done here. KSAN is for address sanitizer. It's done here, okay? And all kind of other goodies that are very important for the kernel to execute but are super architecture dependent are going to be done here. So this is the setup, and actually these things are relatively okay documented, and you may want to actually go and read that. As for start kernel, let me just remind you, this is the x86 case. It was called from two places, okay? So if you look at it, and I know this talk is going to be a little bit long, so maybe I will not address ARM in this one, okay? Because I don't want it to be like 3 hours. I also don't want it to be 2. And when you want break, let me know and we'll take some time. So we saw that it's been called from two places, from head and from head. So the idea is actually to go ahead and figure out, okay, so who starts things? So let me just first prove to you, and let's do the 32-bit case, although it's the same for this and for the other one, okay? The reason I'm concentrating on 32-bit is because I'll probably show some assembly, and maybe some of you learned like assembly of x86 in high school and still remember. And like actually most of the tutorials that exist on all kind of assembly and stuff like that are going to be for x86 32. So, it's easier to find material on these kind of things. So look what we have here. We said that start kernel is going to be called. And yes, at this page, this phase, I can actually go ahead and do debugging. But there are difficulties that I will mention later, depending on the mode, especially in x86. In ARM, it's much, much, much easier. So I'm first showing like where to look. Later, I'll show you how to look like with debugger. So we see a call to start kernel. This call is going to be called from i386 start kernel, which is going to be called from an architecture dependent code, of course. So let's see from where. Going to be called from, let's see. Yeah, so it's going to be called from assembly specific code called head32 in this case, okay? So if we go and look at it, and it does quite of other things that are super interesting regardless. So this is a procedure that is called startup32 that is going to be called after loading the header, and I'll talk about like the phases. An equivalent of it exists in ARM, but this is not exactly this. And as you can see, we have here assembly code that for those of you who worked like with Intel style assembly, read everything in a reverse way. Like the target will always be the second one, okay? So if you are ARM assembler, programmer, or reverse engineers, you will also be confused because when you program ARM assembly, then the target will be the first operand. So we can see here all kind of things that I'm not going to get into too much. But we can see that we have like this data here that is going to be set. And we have like the initial code that is going to be this guy. And we see in start CPU 0, which is a function, and here is the confusing thing. Sometimes you will have entry and proc end, sometimes you will have func start and all these kind of things. You'll have different definitions that are all kind of macros that are going to be in the header files actually in Linux. You're going to have all kind of definitions like this. So here we see that we have a call, right? Call to initial code. So this is like the boot of CPU 0. And when we have assembly code, and we have two ways essentially. Either some line is called and then it falls through, or we call something, or we jump to something, or another architecture we branch to something. So if you want to see who calls this kind of thing, you're going to need to start and look whether somebody calls it, or if there is like a jump to a particular label and so on and so forth. Maybe it's like from another code and so on. Okay, so this startup function is definitely called. All right, so let's see who calls it. So startup32, and I'm just showing you slowly. I can just show you like things. I can put like I can put it like in a presentation, and that's it. But we're not going to do it here. Okay. So if we look like at the code, then we're going to see all kind of physical and non-physical entries. Okay. Now the physical entries, and here you will also see trampoline and things that I will talk about it maybe in a very later phase. Physical entries, essentially, they're going to be discussing real address on something called realmode, or address of peripheral IO, or like real address in memory. And the other terminology is going to be virtual address. The problem is that there are so many different implications to it also in the kernel, because there is logical address, virtual address, and so on. That is going to be what you're going to have whilst you have MMU, for example, in ARM, okay? Or MMU in Intel that is called paging, okay? So these are like the terminologies that you see in the kernel code for that. Let's have a look. Yeah, all right. So, all right. I promise it will be a little bit like more messy, but there's a lot like to cover. So this startup is going to be called, okay? Like you can be 1000% sure about it. And it's going to be called in a physical address. Now, let's look at these two assembly sessions, okay? they are going to be under real mode. And the real mode here, pay attention to what's happening here. It says this. We have long jump. There are 3 types of jumps in or branches like in x86. Something that is like very close, like in the code. Let's say, hey, jump 5 instructions backwards or 50 forward or something like this. And then there are the jumps that are for jump or long jump, that the long jump actually jumps to something that is called a segment. Now, is there anybody here who never heard about real mode or does not know what segmentation is? And I suppose many people are not supposed to really know that. So I'm going to explain a little bit anyway. I'm just curious if it's interesting, okay? So the thing is this. Back in the ancient times, there used to be a 16-bit mode world. And in this 16-bit mode world, and I apologize for those who are ARM only, I started the conversation with x86 for a reason. In this old world, there was no paging, but instead there was something called segmentation. Now the idea is segmentation is this. We have 64K address space, and we're going, instead of just say, okay, so if you have, let's say, I don't know, X bits for the address, then we don't give you, even if you have 32-bit, like in real mode, you're not going to use 32-bit. You're going to be using 20-bit for the addressing. So the 20-bit are going to be divided into an address, an offset. We're going to use, let's say, 16-bit for that. And a segment. Okay? So many times, like in disassembly, you will see something like this, like a DS at some address. So it means data segment at some address. So what do I do? Let's say that I have the following address. 0x, let's say 0, 1, 2, 3, 4, 5. I make it up, okay? Then how do I represent it? With the segmentation framework. So the long story short is this. If it's code, then there's going to be something called code segment, and the same thing applies for data, for extra segment, a general segment, another extra segment, and so on, and stack segment also. The idea is this. I take the value of CS and I shift it. I multiply it by 16, and then I add to it the offset. So this address would be represented by something like CS is 1,000, okay? Multiplying it by 16 will make it 1,000, right? Sorry, 10,000. And I'm just going to add to it the address. All right? So the address of who in this case? Of the program counter, of the instruction pointer, and call it however you want to call it. So it's going to be this guy. So this is how I construct the address. Now back to our subject here. When we see something like this, like the long jump to kernel CS and a physical address, then, or to boot CS and a physical address, it means that it's going to do this kind of arithmetic. Now, why is it important? Because if you want to debug low-level code, you must be aware of this, because your debugger will not catch the things that you expect. Now, different versions of GDB, sometimes you can put a breakpoint like on absolute address, and it will work fine, sometimes not. But anyway, when you want to disassemble something, to see if you like stop on some breakpoint and want to disassemble something, then you would need to go ahead and actually examine like the instruction on $CS, for example, or if it's data, then $DS times 16 plus PC. This is how you disassemble, okay? So these are very important things. So back to our context. I promised you that this startup code is going to be called, okay? Now, I promised you that it's going to be called from architecture dependent code. And this means that it needs to be existing in a very particular place. Now, in order to save time, I'm not going to do the entire walkthrough, but I'm going to jump to the next subject, which actually was a little bit asked about earlier. So, and I talked a little bit more about it also. So we want to see what is actually happening when we boot a Linux image. So I'll start with the end, okay? And it's the same both for x86 and for x86-64, okay? So if I have like, and pay very close attention, this is the build folder of mine. And if I look at VM Linux, let's say xdump-c VM Linux, and then I'll just do head, I will see the 7F elf here, okay? So it's something that I can, for example, go ahead and disassemble with objdump, right? Or with IDA or something like that. So I will see all kind of things. For example, our nice friend here, startup32, that gets a nice address here, okay? Prefixed by C. We learn things from this about the address space, okay? Now, a lot of things are going to be relocated. Some things are going to be in very fixed relocations. We're not talking about this now. Now, this is an ELF file, and this is not what you're going to be loading usually. What you're going to be loading usually is going to be under arc, your architecture and boot. And it's going to be under compressed usually, VM Linux, okay? Sorry. It's going to be busy image, or it's going to be that it's going to be like under arc, or it's going to be all kind of these things, okay? Now, under the compressed, we see several things. And this is the output directory. We see a linker script, which is super important. And we see MISC and all kind of PG related things. We also see head, and we see kernel info and some object files. Now, let's have a look. One folder up. We see things like setup, setup elf, setup bin. We see command line. We see BIOS call. Remember that I told you that we get some things for free from the BIOS. And we see video mode, video VGA, and so on. Now, if you remember the first message that we show when we did like the QEMU with the VGA ask, we're going to see how it was printed and how early in the process it was printed. So those BIOS calls, okay, and like these things that like appear here has to do with the folders that like we examine here, okay? Now, what we also see here is what you expect to be booting, which is busy image. Now, if you look at busy image, it was going to tell us that the file is a boot executable busy image, and so on. Let's look at the beginning of it, okay? So I'm going to look in a very naive way, like with the next dump, and I'm going to do less on it. This was stupid, actually. I just want to do head, so let's do add. Sorry. Let's do 100 lines, okay? So we see a lot of textual files, and pay attention. Setup signature found. This is my panic. Welcome to Ron's demonstration. Boot header says hi. So you can figure out that these things are not exactly from the Linux kernel per se, okay? But look at the addresses here, okay? Here we have things. Then we have all kind of things that go figure what they are, all right? And we have in the beginning some more strings. Use a bootloader, remove this, press this. And I want you to pay very close attention to this, HDRS. Now I want you to also look at the offset here, 200, okay? So that's 512. So here we see instructions and data together. EB is a jump. Now, what is going on here? What do we have here? What does this file look like? Why does this file look like it? What is going on here? So I want to introduce you in order for you to understand what is going on here. And I'm telling you that this is what your bootloader is expecting to load. This is still x86, and the procedures in ARM are very similar, and I will cover them. But I'm not sure if today, okay? I will just give like a taste. So what we see here is essentially some things that we understand, some things that we don't understand. And I want to introduce you first by exploring like the object of it to the header, okay? So if I look at the header here, and I compile, by the way, without debug information, but there's always some things that like help us. If I look at the header here, obj dump dash d to header.o, I see this, guys, bootsec start. Do you see EA05? What did we have at the beginning here? EA05, right? And then 0C and so on, right? So if I look, these are like the code that I see here, and these are like the offsets. So something tells me, like the hunch, and also experience, of course, that this nice fellow here is actually the literal start of whatever I start here. But some things, look, we have sections here. So if the section is like marked as like executable, then I'll also see it, or has like text in it, then objump will show it like here. I can also disassemble with dash capital D, and this will disassemble data sections and so on. And here I see run infinite loop. That looks a little bit weird, okay? I mean, what is this? What is bad and stuff like that? We have set a bad and we have die. That die, look what die does. It moves something to a register, adds something to a register, and calls 74, which is die plus 06, which could be, when we have these calls, this could be like an infinite loop, for example. And many times you have like a call to something that looks weird, and it's going to be symbol that is not yet resolved, okay? So we have all these kind of things here, okay? Now, let's have a look at the file. So if I look at the file, and this file is very well documented, header.s, then look what I see here. So this is assembly, of course. And we have a section that is called bstext. This is why we add bstext. And it's executable, and it's allocatable. These are all kind of like flags for the linker. We have bootsec start. This is why we saw it before. And we have, if we have EFI stub, that is, if you want to like boot from EFI, then we are going to actually go ahead and put MS-DOS header. For those of you who did a lot of like low-level porting in x86 and did EFI, they know why, because EFI is essentially PE, and like it expects like these things. And for those of you who don't, just know that you don't need a bootloader if you have EFI. You can boot it Linux directly as an EFI application. And those of you who don't know what EFI is, think of BIOS. I mean, I will not explain now. Okay, so look what we have. So here we have normalized the start address, long jump to a bootseg that is a constant, okay, that is defined as 07C0, and I already told you what like the segments are. And we have a 6seg that is defined with the prefix of 1000. So if I have something under the 6seg, then the idea is that I'm going to multiply it by 16, add the program counter, and then I can make sense of things if I like want to debug things, okay? So here we have, like, we move like registers, we do all kind of things. We move bagger offset message to SI, the source index. This pretty much indicates that we're going to have a string here, okay? Use a bootloader, remove disk, and press any key to reboot. This has to do with if you try like to boot this boot sector, but it's missing like all kind of things, okay? So we're not actually going to go over it. This is the message loop that will go ahead and take care of this fellow, okay? But there is something that is quite interesting here. Int 0x10. And if you remember, I told you before that there are some things that are like very hardware specific. I don't know but where I put it. I think it was here, yeah. Int 0x10 for graphic services. So we already have like a first indication that I wasn't bullshitting you, right? Now you have also another thing. You have here a keyboard to allow the user to press any key. So this is exactly, to be honest, what you saw like when we looked at the strings of it before in the output it was. So we looked at some of the strings and here it is. Use bootloader, remove disk to press any key to reboot and so on and so forth. Okay. So you actually can reproduce it in QEMU also. I'm not going to do it because these are games. Now this should never return, so we don't even care about it because who even said that we're going to do this code? Now, I'm not mentioning it for no reason. It tells you use a bootloader for a particular reason. You know what is the particular reason? That this is indeed the start of the file, but the bootloader that knows Linux, that expects Linux, is going to jump to a well-known place in the file that is 200, 0x200, okay? So we have here a lot of things in case there is no bootloader. We use BIOS services, we expect it. And now we have definitions. I'm not going to get into it now. Definitions, definitions, definitions. Everything that I have here takes space within within our file, right? So the things that you see here are what is being defined in assembly, okay? So we have these fellows. And I told you to remember HDR. And I was not lying. So let's progress here, okay? So here we have extra, 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 extra. There is some assertion in some place that wants to check that we there is a 497 offset that has all kind of thing. It wants to take care of that. And look what we have here. This is my comment, I think. Offset 512 entry point, global start. This means that the linker will extend this function. And in start, and this is my comment also, don't add anything here because you will expect to have this particular command, okay? That is jump to start of setup -1. What is start of setup? Start of setup is going to be a label, okay? Now, remember I told you about header. So we're going to see header s. So look at this. We have this is 1 byte, and this is another byte. So we have 2 bytes here. Then we have header s, and then we have 20f. So let's see. We start from here. So 2 bytes, header s, and 20f. Okay. Sorry, 02f. I read wrong. 020f. So I'm not lying, okay? Like that's what we have. And I'm telling you that the bootloader will jump to offset 512. It will not necessarily jump to start it. Who knows it? Who cares about it? But it will jump to this address, and this is where we start playing. This is where we start working. This is how things are, okay? So every time you see global, it means it's an external function, which means that there are good chances that you will be able like to disassemble the function and have like a real value for it, which is like pretty good. So that's what we have here. Like we jump to start of setup -f, which is down here below, okay? And look at the comment end of setup header. And look also on this field by build.c. So there are a lot of things here that are being done as part of the build process. And you will find things like ZO and VO that are going to tell you all kind of things of where the compressed kernel is going to be inside the file that you're actually going to be running. So if some of you know, I don't know, like self-executing zip files, like in userspace, then the kernel pretty much does the same thing, but it bootstraps itself. So it starts with some code. There is a header that is expected and needs to be respected, and it's super well documented, okay? It's very well documented, and we're not going to get into it now. If there are requests, I will, of course. But what we're going to have here is where start of setup is a jump to start of setup, as promised. And here, look what we do. We do all kind of things, and we jump to 2F. Now, 2F is going to align a word, then it's going to jump to 3, or if not, it's going to first like do the alignment and then move. And these jumps that we have here will lead us to a place that is interesting. Now it's safe to make calls. That's like my annotation. And one of the things that we have here is like checking a signature. This is a header signature. You're going to find this number defined in another place. But if this one is like not okay, we're going to jump to setup bed. And setup bed, look what it does. It moves the address of setup corrupt, which is a string that looks like this. It's going to move it to the register EAX, and then it's going to call a function putS. Now putS is going to be implemented, not via a library, not via printk, not via anything. I think I will show it. Like if it's interesting, then when we disassemble some things, maybe I will show it. But this is like an indication of something that looks like normal for the normal programmer, right? We check a signature, we compare in AT&T, sorry, in GNU syntax. Yes, in AT&T syntax, it's and not in Intel syntax of assembly. Then you're going to do operation and you're going to provide a type. So long in Intel, it's confusing. It's 32-bit. Okay, quad is 64-bit. All right, word is 16. I mean, it's ancient, but it still is. So here we add like comparison and jump if they're not equal to something that prints. Okay, here we zero the BSS, and here I have something that I made myself. Like I added a header and I called putS. And if I did something like this, jump to run infinite loop, I'm going to look at the message right now. I save it, okay? And pay attention to the next line. You see call main. Main does things, but now it will not do it because I put an infinite loop. I print a message, call, boom, to my thing. If I did that and made my kernel, and I'm not even bothering to, I hope I'm doing it in the right place. I'm not even bothering like to paralyze the okay, I did something bad. So let's okay. There was a question, I'll see, or there is some comment, or there was some joining request. Yeah, simply. All right. Okay, so I'm going to like rebuild it and that's it. Okay. So here I add my environment set. So I'm just going to it's going to change the directory, build kernel. Yeah, I should have used like the old config over there. I know why. Okay, this doesn't look good. Hold on 1 second. I did prefer it before. Yeah, but you know what? I'll just rebuild it and that's it. Because I changed it, because I started building, I changed the config, and then I did something. Never mind. It's going to be a very, very, very short build anyway. The reason I did the change is because I know for sure that like the minor modification that I made is supposed to be like super, super, super fast, and it's just going to like link. Okay, so I'm going to now build it, and I'm going to soon enough go ahead and show you like what I'm going to actually show like how it's going to be called. All right, so you know what, now let's take, I'll give it some time to build. Are there any questions or like any comments? Like, do you find this interesting? Do you find it a waste of time? Do you want to concentrate only on ARM? Are you happy? Are you upset? Can you even hear me?
I was having problems with my mic. I don't know if you can hear me.
Ah,
Can you?
yeah, I hear you perfectly.
Yeah, no, this is awesome. I've been really enjoying it. Yeah, I would be awesome to see ARM at some point, but it's also interesting to see x86 since that's what my laptop is and servers and everything.
So Omer, your request is, unless you can convince me that you know everything here and know how to do, if you know how to do porting on any x86 platform, then your request is respectfully denied. Okay, so yeah, but we'll get to ARM. The reason that I start with this is that BIOS give us a lot of things and it simplifies things in terms of understanding. And because when you want to teach yourself with a debugger, it actually makes things very, very, very hard comparing to ARM. So when I do like very long-term, let's say, courses, then I have a lot of time to go with my guys over it. But in like a workshop or things like that, it's not really possible. And now we have the time. So okay, so it finished building, and I added this infinite loop, and I really hope that I didn't mess up, right? But let's have a look. So here is like this append VGA ask, and look what's happening. Infinite loop. Welcome to Ron's demonstration. Boot headers say hi. Right? I'm not calling main. I'm not doing anything. Like if I undo what I previously did. By the way, Omer, I was of course joking. The reason I said it is so that you will deliver another talk. Now, but you did your part last time. Okay, so, and it was great. So I will rebuild it, okay? And look how, I mean, it didn't do anything now. Look what was affected. Check it out. Compile.h, never mind. Generation of makefile, never mind. We assemble header.o because we modified header.s. We link setup.elf, and we obj copy setup.bin, and then we build busy image. It means that, like, honestly, it means that many things were not changed, but I will explain it when I explain how the images are built. And seriously, the reason why okay, I need to tell you something. The problem is that it's recorded and it's so long, but I need to tell you one thing, especially, Omer, אני מקווה שאתה עוד איתנו, I hope you're still with us. Because what you said now is exactly what I always said. Exactly. You're still with us? Okay. Never mind. Yes, no. retry, abort, fail. Anyway, when you come back, then I'll I'll explain why you know, in a hindsight, I think that first of all, especially since you do automotive, just know that Intel does a lot of automotive. But Intel platform are great because the initial bring up is done for you. And like, I don't know, a couple of years ago when I was doing, it was mostly for Android, supporting Android research, things like that. Courses that were very, very long term. Like, I'm not talking to you about week, I'm talking about months, right? Then I would just focus like on one architecture. Usually it would be ARM, to focus on what matters. But to understand and teach yourself things, especially since we don't commit to a schedule here, understanding the origins are very, very, very important. Now, as I told some of you in one of the previous meetup that was still like physical, then the kernel code for Linux 1.0 or something like this is great because it's not huge and it's much simpler to see things. However, you will not be able to make it build like immediately. So a good thing would be like to consider something that exists. So I changed it after like all these things. Maybe I should cut it like on the video. And now if I boot it again, I will not have the infinite loop. You see, I have it like only one time. So we're convinced that I wasn't bluffing, okay? Now let's have a look at this guy, setup elf, setup bin, and the likes, okay? So let's see who changed last. Busy image, of course. Here is the command for busy image. So when you go and want to see how things are, and guys, it's important because in ARM and in every architecture, the procedures are the same, okay? So look what we have here. We have here like, this is like a tools build, setup bin, VM Linux bin, Z offset, and busy image. So this contributed to the building of it, and the build script will actually go and take care of like this, okay? Now, this is for this, for example, if I want to have a look like at what I actually did, now header.o command, then here I have a lot of other things, right? So we actually see that we use GCC over here. We have all kind of we actually use the assembler, of course, but GCC knows to use like assembly, like you can invoke GCC on an S file. And here we have like the includes and the dependencies and so on, okay? If we look at setup elf, and I do it deliberately, I'm going to show you like the relation between the binaries and the health. So it uses LD, it links, and since it's a 32-bit platform, then we link here. So what do we link? We link all these fellows here, right? Video BIOS and video VESA and video mode that I mentioned for, and BIOS call that I mentioned for a reason, okay? The command line and so on. And you know, anybody, let's make a quick quiz. Anybody want to tell me what would be setup.bin? Okay, so setup.bin is going to be this guy. Opt copy. So we have opt copy -o binary, setup elf, and setup bin. Now, actually, Eyal, this is super relevant for you, like all this kind of thing. The reason you may want to understand like the different phases is if you get like unknown file that was dumped from some memory and you want to make sense of it, then you want to understand the process. Now, in order to understand the process, what I usually advise is to pay attention to a nice file that is called scripts extract Linux, VM Linux, that is going to check whether the file itself is a VM Linux that is an ELF. And if not, it's going to try to decompress Now, there are well-known positions for the compressions, and it's going to go and search for some magic headers. So I configured my kernel to only support XZ. I'm expecting to see this somewhere, okay, like in the file. And it's going to go ahead and extract something from a very well-known place. So if we look, for example, at setup elf and setup bin, then we could see extemp. Let's do it as a char to set up bin. Huh? Oops, I piped it. This was not my intention. Then we can see that it looks exactly the same as what we explored, right? So setup bin finds itself exactly as is in VM Linux. It's very important, okay? And let me remind you, it was prepared out of setup elf. And setup elf included our changes to header.o if you caught it in the linker script. So if I disassemble, if I do, you know what, just for fun, to set up elf, here I will see elf header, and I will see strings in all kind of places, but I will also see additional data and of course different offset. Why? Because this is how elf looks like. And if I had like debug information or like the symbol information, then I would have them like somewhere here or so on and so forth. I can go and look on if I want to see what's happening here from a reverse engineering perspective. I can go and like, you know, see what the segments are and so on. By the way, I mean, I know some people may disrespect a little bit that it's 32-bit Intel. So two things I have to say about it. First, it exists, right? People use it. Second is that in 64-bit, it's the exact same thing, exact. So, you know, we have our kind of thing, and we have symbol table, and we don't have debug information here, but, you know, it's enough like to be able to do like remote debugging if you can, and so on, okay? Problem is that you need to know like the addresses. So we change this file, and we know what the header does. We are convinced that the header is what is starting the entire operation. Now, under the header, the nice header that we had, if I commented out this stupid infinite loop that I made, we have call main, and this should never return, okay? So let's see what is call main. Now, if I go to call main, and by the way, you don't have this in ARM, and in ARM you will have add.s that will have like a s-text function that will start all kind of things. If I go to main, where is it? Yeah. If I go to boot main.c, I actually have a main function. And there I, again, called putS, this time not from assembly, run 0. I also called printf, print k, run 0, okay? And I put s, run 1. And look what I have. Like, if I didn't add this run, and I wanted to see that this super early code is being executed, I could provide a kernel parameter called debug. And then I will see, hey, early console is setup code, okay? Now, something very, very, very important. If you want to see the text, there are several things that need to happen. You need to have a console, you need to have your UART set, you need to have a way to communicate with the external environment, okay? So even before we had like a console, I could print some messages to the video BIOS, okay? Now, why? Because I used the BIOS routines. So the difference between having support or not having support could be looked, let's see it with something like this. Like if I do like no graphic, I will need to also provide a console. Early console equals y0. Sorry, I need to provide early print k, and I will need to provide debug. And I need to provide console also. So console equals tty0. Early console, actually, it's good enough. What did I miss here? I think I still have a. Do I still have the infinite loop here? Let's see. No, I don't. Actually, I'm not sure what I missed here. No graphic is okay. Sorry about the delay. Like handling several things. Okay, I think I know what is the problem. Maybe I changed the configuration of the kernel. In this case, then we may have undesired solution. 8 to 50. I'm seeing, yeah, I don't have serial console. You see what's happened here? Like I don't see anything in the no graphic because when I rebuild the kernel, okay, I know what happened. I added it like my build config. It in this particular branch, it did not include support for serial. So I'm going to fix it like in a second, just so that it will be more. First of all, it's like a nice exercise, like to see how to debug things. And the second thing is that let's see. You know what? I'll do it later. Like maybe we'll take a break because I want to show the BIOS thing. I just want to tell you that like this early console. Sorry for like the for the confusion. I don't think I would. Yeah, cool. So I will take care of it. I did like during the talk, I made a build that like reset the configuration that I had. By the way, if you want to see like what is different between different configurations that like you have, you can do something like this. Let's say that if I have here several config files and I do diff in config and config.old, then this particular version is not saying so much. It automatically added, because I did build twice, so it screwed up other things. Like, look, it says like the architecture was x86 as opposed to like i386. So because of that, it felt like the need to generate, even though they're like the same. Okay, so I messed up here. But in general, what you would want to do, then there is going to be a script that in your kernel source tree, once again, so it's going to be under Linux, script diff config. And if you run it, then look what it does. It's going to tell you, hey, like in this current configuration, what I did was modifying 64-bit like to know. And there was a difference in the parameter that went here, this way, like from 400 to 0300 and so on. Okay. The reason for this is that I generated the configuration in another, like I took it like from the GitHub and it was done like on another laptop. Okay. So back to our discussion now. Now it's definitely like not suitable for like uploading the video or something like that. It became like too long and with too many like so-called interruptions. But you can, if you think I should upload it, I will. Why not? So we were in the
I
place
think
where
you
we
could definitely upload. This is super helpful. I would definitely want to rewatch it.
Cool. All right. So have a look. So like what we did, we proved that that under arc x86 boot, that if we change like this head, then it finds itself running because it was like in setup elf. Then it was stripped using garbage copy, like we got rid of the container of the elf, and it was put just as is in the beginning of busy image. That's what happened here. Okay. Now, this main file that we started looking at, And I sorry, like, so we saw like this print case, and we see the console in it, and then there was like this detour where the serial was not enabled, but I'll do it later just to prove that I'm not lying. But look what kind of things are happening here, friends. We have here, and this is the x86 boot code. You will not have it in ARM. We validate like a CPU. We check that we have like support. We set up a keyboard. We set BIOS. We set a CPU mode for that. And then we have these two very, very, very important functions. Okay, this one nice function and this one super important function go to protected mode that I will cover later. But look what's happening in set video. So when I disassembled, when I showed you like what were the commands for building, when we had a look at the whatever dot command, we reasoned that one of the friends here was video mode. Okay. So let's have a look at what this video does. Okay. So let's have a look at video.c. So we're not going to actually go ahead and dissect everything, but we have a stored cursor position. So it probably means something, right? To store video modes, and we have something that is called BIOS reg. So we can assume that we have like communication with it. We have store mode, and we have all kind of functions, things like that. And sooner or later, we will call BIOS entries, okay? So we're not going to actually look at these things, but I want to show you human readable things like put S mode resolution type. So it's going to enumerate like the different modes. And this is the first menu that we saw when we had like VGA. And before it, we had this guy, press enter to see video modes available, right? Space to continue or wait 30 seconds. So these things actually happen, and as well as enter video mode or scan and so on. So they happen very, very, very early in where we operate, correct? So we have some hopes of actually seeing something. We already know that we see the prints, and when we do like debugging, then I'll actually show you how we see it. And we see that things actually like make sense. This very early setup code, which is great. Let's once again run a QEMU just to show you again, to refresh your memory. Here we see like this booting from ROM. Press enter to see video modes or to continue, and this is like the table mode resolution type, right? So I did not lie. Mode or scan to scan initial modes. So I did not lie, but this is what we had, right? So 1-to-1, right? Great. Now we were at it when we were looking at main.c, where I said that there is a super, 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 super important function. Go to protected mode. So remember I told you about like the segmentations and stuff like that, and I said that like an important thing that we need to do in ARM and x86 and everywhere that supports MMU. Linux also runs without memory management unit. So Linux actually, sorry, there was a little bit of a, somebody wanted to ask me something, sorry about it. So Linux runs also without memory management unit. And there are projects for that. It's actually part like of the kernel also. UC Linux, Micro C Linux, whatever. There are userspace versions for it that has like libc that lives fine without MMU. And there is non-libc version for that. And can also talk about it some other lecture. But in general, Linux is made to run with systems that has memory protection, and that has in particular MMU. It is not MPU like if you use some microcontrollers or Cortex-R for ARM, but rather MMU. Okay. So go to protected mode. Is going to be in these guys. There is PM and there is PM jump. Okay. So PM jump does like the real thing. So we have protected mode jump here. So we will once again see like all kind of sectors and things like that. Okay. So we have this nice guy here. Actually, this is the jump to the kernel. I expedited what I wanted to say a little bit. And we have this PM that is going to do all kind of things that should be relevant like for you. So here is go to protected mode, and look what's happening here. Here we have indication that we were in real mode. That is the 16-bit mode where you needed to have like a segment and then like the program counter. And we're going to mask all the interrupts and set up the interrupt description tables and then do the protected mode jump. Now, what is the jump here? Check it out. We have here boot params header and a function pointer to code 32 start. Okay. So this protected mode jump is going to actually go ahead and do the changes to our addressing mode that is no longer 16-bit mode after we enable the corresponding register in the, it's not in ARM, it's coprocessor, in the control registers, okay? In the control registers. So there are control registers that are responsible for enabling paging, enabling memory protection, enabling these things, and that is how it is. So the easier things, for example, to set up like the IDT, we start with an IDT that is not really saying anything, and later we're going to set it up. So these are the command inline assembly for actually doing this. So check it out, like null IDT doesn't say anything interesting. Here we are going to set up. This is going to be the assembly call LIDTL with the address of this guy. Okay, so we're going to do that. So this is like another setup that we do. We set up here tables. I'm not going to talk about it too much. And out B is going to be like writing to some port, for example. So here are our mask like interrupts. We're going to write here. And the switch, like we have like the jump here. And we jump to code 32 start. So you can go ahead and see who actually sets this function pointer, okay? Now, the moment we actually have the paging infrastructure, then we can do everything that you expect to do in the kernel, okay? Now, I remind you, this is the early code that is happening. And we're almost 2 hours like in the talk, so I think I will either take a break or like I will take a break soon, and then I'll show you some debugging, and then like we'll call it a day. But there are like everything that you need to see is literally here, okay? Under boot or under kernel. So you would always want to go ahead and like grab. So for example, like if we look at PM and you are curious, okay, so where is like real mode switch hook and who takes care of it? Okay, so this is in this particular file. But otherwise, if you want to do things that are like, if you want to see where is like the start, the code 32 start, who assigns it, and what are like the boot params, then you can go ahead and just search like under the corresponding folder, like under x86. There are not going to be a lot of it, okay? And eboot is for EFI boot, if you're curious about it, okay? And here are like what we have here. We have boot params, okay? Code 32 start. And if you look at the header, this is not what I had in mind. So I want to PI this guy. What did I do wrong now? Huh. Okay. So you can find your way in it. This is what I'm trying to say. So you're going to have like a setup header and like version and all kind of like pointers and enums and things that like you expect, and they're going to be filled out like around the way. Now, if some of them are going to be filled like by the build process, like for example, if you tell it like where to load like the kernel, some of them are going to be filled by like hard-coded in some places in the code, and some of them are going to be filled in the header that we saw earlier, okay? So I'm not getting into more details about this, but the jump is going to be, and some are going to be filled by the linker. So I'm not getting into more details here, but things make sense, okay? And you can, it takes time to show everything, but like things really, really, really make sense. Speaking of the linker, like the setup script for this, for the setup, it looks like this. We can see that the entry point is, the expected entry point is going to be underscore start. It is under the header that we showed, okay? And here we have sections and offset. And check out this assertion. We are expecting that a particular word will be in a 497 like a offset. Otherwise, we say, hey, like something here is like not okay. This is like in the linker script, okay? So that's what we have. The signature that I told you that is set somewhere else, the linker sets it, okay? And you need to learn a little bit like about the language of the linker script, but for most things, it's pretty much self-describing, okay? However, something that is not so trivial, and pay attention, here I split the source from where I built things, is that there are automatically generated linker scripts as well, okay? So if I go like to compressed here, I will see there is vmlinux.lds. So we can see that the entry point here for the VM Linux NDS is startup 32. It's going to be called somewhere, our data compressed, and so on, so on, so on, so on. So there are some confusing things here. Let's put it this way, all right? And it's very important to know, like, what is happening when and where. Now, last thing we said is that we have like protected mode. So we had like this go to protected mode. And let's have a look again at the header. Sorry, at the, we had init.main. It's called, I'm in the output directory. So it's called protected mode jump. All right. Which is this one. Okay. So basically, look what we have here. We have like, we modify CR0 protected mode here. Okay. And this essentially is going to tell you that like, hey, you are like setting like paging and things like that. And then we jump to the 32-bit entry point, which is set in one of the register here, EAX. Now the question is, all right, great. So who calls this? in_PM32, in protected mode 32. So these are like local labels, okay? So we can see that if we look at head, that is expected to be under the compressed folder here. Kert32.s. Then we're going to have like the startup 32 function. Okay. And okay, now I'm going to go like very, 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 very quickly. I just want to tell you about some keywords to pay attention to. So one of the keyword is relocatable. Why? Because when we load the image, like the busy image that we load or whatever other format of image, we're going to load it into some place that we're not necessarily knowing where it will be loaded. And we're going to, the code will actually, we're going to copy, we're going to extract the kernel from somewhere. So we see here like things like relocation and decompression, and copy the compressed kernel to a buffer and relocate and decompress or uncompress or things like that. Do the extraction and jump to the new kernel. So what we have here, and it's a very long story, very, 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 very short, is that we have load address of input data, and we call extract kernel. And look what's happening. The comment says returns kernel location in register AX. This is cleaning up for the stack, not interesting. Zeroing VX, and then we jump to this guy, to EAX. So what exactly is happening in extract kernel? What is extract kernel? Why is extract kernel? So here we have several nice things that are helpers. Let's see the question or the comment. Yeah. Yeah, so there was a question. Soft MU, you meant what? You meant about the MPUs? Itamar. Okay, I think we're running too long now. And I was expecting it. I told you, like, I mean, I was definitely expecting it. And I deliberately didn't bound it, like, since I'm like the only speaker, I deliberately didn't bound it to be like, you know, like with an organized agenda necessarily. So I'll do like yeah, so it's possible. So you can look at, if we talk about ARM, add MMU, and yeah, add no MMU. I still didn't get to the head, and then we can like cover it. So sure. So I think I will tell you like where we stopped, friends, and I'll publish it, and I think we'll like give it like another go perhaps later. Like maybe we'll continue another day or something like this. But or maybe the important thing would be to not dive too deeply. But I want to say super important thing here, like super, super, super important thing. That extract kernel is going to do the following things. Going to be under MISC. And it's going, there is like a nice diagram here. Like we have a compressed kernel image that is loaded like to memory. And our objective is to have a uncompressed kernel image. So the idea is to extract the kernel, whether it's like in XZ or a tar GZ or BZ2 or I don't know what, okay? Debug put str, you will see it if you have early console kernel parameter enabled, okay? And you enable the debug level, that is you increase the log level of print k to 8 to 9, okay? And every time we have like put address or put, these are just prints. The important thing here is that we're going to extract the kernel with decompress. This is the decompress in Linux method that you may know. We're going to parse the ELF file because the extracted kernel, what we have like in the busy image, is actually a representation of what we have in the VM Linux. By the way, in the top directory, VM Linux also has debug information. But when it's stripped, it's going to be compressed and put in the busy image, okay? And what we're going to have here after we parse the ELF, we know what are the relocations, the expected relocations. So we take care of them and return the output. And what I told you in the previous one is that we jump to this is the output, EAX, okay? When we call something, the result is going to be in EAX, and then we jump to it. And this is where we have like the kernel that is already like an organized elf, let's put it this way, and is in protected mode, and we can do pretty much whatever we want here, okay? So this was head 32, and start kernel is not here, okay? Why? Because in head 32, whoops, where is, I'm looking for the C file. Supposed to be under here, no? Ah, sorry, it's under kernel. Sorry, my bad. So head 32 .s is actually another instance of that. It has like the startup code that is, and head 32 will be called by it, and like it's called like i386 start kernel that we called start kernel, which will get us to what we showed in init main.c. So I usually, break like this demo into much more hours and show all these kind of things. And if it's interesting, I will dive into some of those. Okay, just one last word. When you see the zipping procedure of like the boot, like in compressed, you see MISC that has the decompression code, and you also have make piggy or piggy.o, piggy data, all kind of things like that. You will have them in every possible distribution in a architecture, okay? And make piggy is actually, check it out, it's an assembly wrapper with the appropriate symbols defined. Look what it does. It's a user space program, this make piggy, okay? This is what it is. It gets a file for a compressed kernel. And what does it do with it actually? The idea is that this make piggy that here is under compressed. Here is this fellow here, right? It contains this piggy.s, and look what we have here. We have here like input and output. Pay attention. Of these fellows. We have the length. We don't know it ahead of time. So only after we build, we calculate the length. And we include VM Linux bin.gz. Okay? So let's have a look at this. And we also have, because I chose kernel decompression, like the kernel itself is going to be an XZ. This is support on the kernel itself. It will actually include the XZ, but never mind. So let's say if I do like make dir temp, and I copy VM Linux bin gz to temp, and I look at it, and I go do unzip on this guy, then I will have VM Linux bin that is an elf. Okay? What is the file if I look at VM Linux bin prior to it? Elf, exact same thing. So I compress this guy. Okay? So what I compress here is the elf, and this is why I could parse elf. I mean, we're not with a board, and I'm not, showing graphics and things like that. But this is how we parse it. So piggy helps me to piggyback the Linux elf code, which is added to the setup code. Okay? And the setup code is aware of the decompression that it needs to do. So it's going to go ahead and pass control to these nice fellows here, and that will decompress the kernel, that eventually will jump to start kernel. So that is like the road. Okay. So the same things happen also in ARM. I guarantee you the same things happen in ARM. They happen everywhere. And I just want to show, I was dying to show you some debugging with ARM. Maybe I'll do another meetup tomorrow. I don't know. Let's discuss it like after I stop like a recording, and then I will show. Because by the time we do another session, I will forget what I want to talk about, right? This is why I like encourage feedback and stuff like that. I do prefer it to be, people jump over the mic, so I pay attention. But let's have a look here. So where were I? So now I'm going to do something a little bit different, okay? So this is the big picture, more or less. And we saw in several places that there is like put s, for example, that has been used. And there are definitions of these functions actually in several places. So there's going to be, if we go like to boot, so we have something like tty.c that implements some things. And look what we have here. Like we have BIOS put char. And what do we have here? Some registers and int call. Int call 0x10. It's of course a wrapper that we implement in Linux, but just pay attention of it. Here again, we have put char. So put char, maybe we'll use the serial, and then there is like another indirection. And put s does a loop. And for each one calls put char. We also have get time. Now it's the one A BIOS service and so on. X16, remember? So we have get char. So actually there is duplication of this code in several places. But we do have this, okay? So these are some of the things that we have here. Now, let's go to our output here. And now I'm making a very long story short. I actually wanted to exhaust you and go and show you how somebody who addresses the problem without having additional knowledge, and the nightmare they will find to actually go and find the relevant instructions that they want to debug in real mode, for example. So bear with me. This is ELF, so it's like easy. And one of the problems, like if I look at setup.bin, is that I can't use objdump on it because it also doesn't have like information. It has addresses and that's it. I can go and make sense of it with a disassembler like a IDA Pro or like Ghidra or like with another disassembler that never mind what it is. And I can go ahead and look at some things that look familiar to me if I use objdump, okay? Now I'm going to give you a very important tip on x86. In ARM, everything is like super, super, super easy, fortunately. And I made a mistake to disassemble everything. But look, they're like nicely organized. We see go to protected mode. We see the assembly code here. So we can search the memory for the instructions, and then we can like find out where things are, like when I'm like on a debugger. And we can also take advantage of us knowing like the sequences and addresses of functions here. Now this guy is going to be relocated. So if the address like on the file itself is, I don't know, 2E9, then nobody promises me that it will indeed be in address 2E9 in the memory. But fortunately for us, then the system segment is at address 0x1000. So from the calculation we did before, we multiply it by 16, and we're likely to see like int call, for example, in address 10,002E9. And we can see like put char, and we can see put s, and we can see all kind of things like that. So let me show you how we actually go and debug these things, okay? So here it goes. I'm going to go and do two things. The first thing that I will do, yeah. So the first thing that I will do will be to go and what do you say, guys that are here? Should I do it now? Worst case, I will continue another day also, but I want to demo. Like, worst case, I will repeat. Okay. Anybody still here? All right, all right. Like, yeah, thanks. But it's embarrassing. I need to hear. It's embarrassing, like to show the chat and see, like, hey, people went down. But for anybody who didn't attend the meeting and hear this, then I just didn't really publish, and then of course Google Meet streaming didn't really work. But all right. Okay. I also forgot to ask you that if you take notes, to maybe send me some so that I will put it like in the description. So because I will not necessarily remember what I did, and I don't believe I will be watching the video again. Uh, so here it goes. All right. So this technique that is super applicable to ARM. And by the way, Drew, like for BeagleBone, one of the nice things like with Yocto is that like when you build the image for BeagleBone, you can just do like run QEMU, and it will run QEMU on the image that you built. So of course you don't have like all the peripherals, but QEMU emulates them like nicely. We'll keep ARM for another time. Yeah.
That's interesting. I never thought to use
It's
QEMU.
amazing. It's
Yeah.
amazing. It's not interesting. It's super awesome. It's really awesome. So,
Nice.
but I also didn't know that. Like, I mean, I knew I was doing it manually and doing some adjustments because like ARM is ARM, but I didn't know it like until like 2 weeks ago when I was preparing my Yocto project class. And I did it on a newer version of on Dunfell on a newer version of Yocto, although maybe it was also like in Zeus. And like I did the script and it said, hey, like it gave like the note also like for the bigger one, you can run QEMU, and I said, all right, and I did it and it like worked. So it's pretty cool. Like like before, I would keep two different configurations and a lot of disk space, and it sucks, right? So where were I? All right. So I want to show like about the debugging. So what I need is two things, okay? And I'm going to do what I need is two things. The first one will be but yeah, VM Linux, just so I will have, I don't even need it, to be honest. I just need like to know addresses, but I'll GDB with it anyway. And I will need to connect to a target. But before I even do it, I will just have some stops. I can make more advanced scripts to show me the following things. Let's say 20 instructions off a code segment times 16 plus program counter. And I will also add to show what is the code segment. Now, I warn you that sometimes GDB disassembles things the wrong way. So it can take days to figure out that the mistake that you thought there is not even a mistake. It can be like terrible. Like IDAPRO does better and much better work with realmode in it. And same things actually also are true for disassembling of GDB of some ARM versions, families actually. So maybe it's a subject for another talk. So here goes. Where am I? So I wanted, so here, this will be my debugger window, okay? And on another one, I will go ahead and maybe I have history, yeah. So look what I do. I run my kernel and I give it -s and -s. This means that now this is stopped. I will put it always on top so we'll see like some output. Now we'll split the screen, okay? I'll put it a little bigger. All right. So this means that it's expecting a remote debugger to connect to it. And since the default port will be 1234, I need to do target remote. And I was planning, so now it actually does something. Let me just prove you, like if I do cont, then it will continue, all right? So I will close it, I will detach. And one of my plans was to show you how to do like reverse debugging, but it's something that doesn't necessarily work always with remote, and like see how to figure out some things, but we don't have time. So I'll just show something. So once again, this trick, I wasn't bluffing. I'm going to put it on top just in case. I'm going to do remote again. And yeah, so this is my tab stop, okay? But I can, if I look at like the current and look like at the, and I did a mistake. I wanted to show it in X. So on display 2, I'm going to do display /X dollar, what's its face? Code segment. So now it's in F0000, but maybe it is in real mode. Maybe it's not in real mode. What I'm seeing right now, and now I'll do just on the PC, is QEMU code actually, okay? So I don't have any breakpoints here, and I don't have like anything like really too interesting, to be honest. But I'm going to start jumping and seeing what, or like single stepping and seeing what's going on. Okay, so if I do step instruction, we see that now this is like the segment, and now it sees some other things. But I need to tell you one important thing. What we're going to be run now is QEMU code and the BIOS. And the BIOS, as well as the initial Linux kernel, are going to be in not in i38.6 mode, but in 8086. So if I go and see these things, there are chances that I will see different commands at some times. Now, the bad thing about QEMU and real mode is that they don't like each other way too much, and you need to do a lot of things manually. Some versions of GDB, when you are able to put a breakpoint, they do not behave very well, okay? And like I could go and, you know, step instruction or next instruction and step a lot of these and see what's going on, or like step now, I don't know, like 20,000 instructions and hope that something good happens, or step 200,000 instruction. Can you see like in the right side, QEMU stopped and stuff like that? I could do that. But what I want to do is to figure out where my code is, okay? This is my intention. So one of the things that I can do is go ahead to what I saw earlier, like I'm going to, you know, let me, but I did opt dump. Let's go back. x86 boot. And I did do opt dump to this guy, right? And let's say that I want to see put C or put S. This was a mistake. So let's see what happens if I want to put a breakpoint like in 3D2. If somebody calls like put S. So I'm going to resume the execution of GDB. Something here is off. Oh, I did several enters, so it repeats the previous command. This was a very bad mistake, but I will detach the tar. Ah, okay. I will detach the target and then do it again. And then it will be okay. You see like some of like the things that can be like very annoying when you do things. But now I'm going to go and try this. I'm going to try and put a breakpoint in the address of put_s or close to it. If I go and do it like this right now and continue, I will not stop. Now the reason for this is that this is not the real address. Now, sometimes for some version of like GDBs and QEMU, it will actually break at any place that the program counter is this, okay? Now we don't really know that the relocation of this is going to keep the same value, but in this particular case, and now I will exit it and do the append and target remote, and I will delete all breakpoints, yes. In this particular case, I actually do know that the code segment is expected to be 1000x. So unless GDB doesn't like me now, which is okay, it's a possibility. So maybe it didn't break exactly like on this one, okay? So, or maybe nobody called put_s here. This is also like an option. So I need to start to see like what is really going on in these things. And what I would want to do is to like search addresses that I know for sure that are being met. Or maybe a breakpoint will not do and I need to put like hardware breakpoint, and here like I put on. So these are like all kind of challenges that you are very expected like to meet when you do these things, okay? So these are the things that like, let's see. Yeah. Sure. Welcome. So these are like the things that you expect to encounter, and like maybe addresses like change like on the final link, maybe something like this happen, maybe you're stuck in I don't know where. So like your procedure would usually be like now, where is like the QEMU? Your procedure can most definitely be, you know, stepping instructions, you know, do binary search on how many instructions you want to step next. Let's just do it like for fun, like 100,000 instructions. It will be quite a lot. So it will run, it will run, it will run. And you can go and search for things, or you can go and search for a pattern in memory. You can also do that. But you need to have all kind of like, you have to have like an estimate, like an intelligent guess, okay? You don't need to just go and say, all right, so maybe I will step instructions like this. So some of like the things that can be interesting for you are figuring out where there is like all kind of call instructions or return instructions or IRET instructions. So you can search like the opcode for them, or you can search like the opcode, search like the binaries from what we saw like in the code itself. And then you need to, like we did like in the extemp or something like that. So we stopped somewhere. I have no idea where we are, okay? But we stopped somewhere. Let's see what is the architecture. In ARM, you don't have these things, okay? In ARM, everything is okay. You can go and like put a breakpoint in like the first point that you meet, and end of story, okay? And you can like search like for the calls or things like that. Another problem, you will not really have like a backtrace. So if you like, because the programming here is not according to ABI that you would like expect probably. So remember we said, hey, there is like these headers. So we can go ahead and do something like this. We can do the find command. You can see the syntax here. Basically, it's going to take like the size of a char. Okay. So it's going to be find slash, let's say 1 byte. And let's start from this address to this address and hope that it will work, and search for Oops. Search space. Oops, this was wrong. So pattern not found. Maybe it's header S, or maybe it's not. Or maybe it's not like even in this address space, okay? So these are like the kind of things that like you're going to find yourself having challenges with, okay? Now, I know the answer, don't worry, I did it like yesterday. But the thing is, and what I was like looking at now, like this is what we're like trying to figure out. Like, so we have HDRS. So maybe in memory they appear like not necessarily in this order. Maybe they appear like in another order. Maybe I would want to go ahead and search for like the word 20F. Maybe I don't even know where the memory is loaded. These are like the kind of challenges that I have, okay? And this can be very annoying and very frustrating. So I now single step like I think 100,000 times, right? I did like next instructions. I can go and proceed with it, like do, okay, let's do another next instruction and things like that. The problem is that a lot of time I will do these things. And if I have breakpoints that are active, QEMU will not work well. So this is one instance of an annoying problem. There's a possibility that I did like hundreds of times or 100 times next step, and it didn't even do one step, okay? These are like the kind of things that are expected like to happen. And so I will delete this breakpoint, delete all breakpoint. Yeah, why not? I will give it another try. I'll say, all right, let's try and do like hard breakpoint in, I don't know what, in hardware breakpoint. In, let's say, 0x. And 3D, by the way, what was 3D2? Let's say 3D2 or 339 or something like this. 10.339. And I need to put the address, of course. So again, like no luck here. Something here did not work. So this kind of like challenges are the kind of things that you would encounter when you go and actually face like single line debugging, and getting to the point that you want can be very annoying and very challenging. Okay, so I just want to know if there are like other questions. So before I actually go ahead and revisit like the addresses and see and show together how we're going to take care of that. Okay, now I just did a break. Now we are in the Linux kernel when I debug. So things are, I'm way past init. I can go and put, for example, hardware breakpoint on, I don't know, to exit and continue. And here, like, I have backtrace, and here life is good. And, you know, because I returned for fork, I have like this to exit, and everything is great here, okay? So this is like a completely different story, all right? So are there like any questions? I think like I was planning to end it around 8 p.m. this time, and it took a little bit more. Okay.
So do you ever do it with an actual target, like a board over JTAG or something like that?
Like what?
Like with a board connected over JTAG?
Yeah, of course.
Okay.
Of course.
What
But
equipment do you need to have that connected to, like a ARM board or something like that?
for?
If you wanted to do GDB remote debugging.
Yeah, you can also do it in Intel. It depends. Like it depends what platform you have. But like for Intel, you don't really need that. Like for Intel, what you're going to do, and this I showed in some of like the videos I put some things in like some channel and some YouTube channel, and it was very, very, very bad. I took it like from a cellular phone, and it was like what I did there. Like I actually had like an old laptop and like an old computer, and I connected like a serial just to show that like when I talk about QEMU on x86, and I'm not bluffing. And like I was talking there about like a remote debugging with KGDB, for example, but there are hardware debuggers for x86 also. If you need to do something very, 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 very low level, and if not, then the moment you have like the moment you have initial kernel that is running, and in x86 it's much easier to achieve. And nobody does it, to be honest, because this problem is solved. Problem of x86 is solved. All x86 platforms behave in the same way in their initialization phase. There is no need or reason for anyone to ever deal with like the setup code. Okay.
Yeah.
So, but
I'd love
when
to use like KGDB with like the BeagleBone, but I wasn't sure what. Do I just need a serial?
you need the TTL,
Okay.
use KGDB. Yeah, you need a UART. We can talk it like another time. Yeah. So so I was going like to check the addresses now. So if I look at its setup, this is like the one that like really interests me. Okay. And I go and do, let's say, opstamp on setup.elf. Start of setup. Int call is 2e9. That sounds promising, but there is a good chance that the offsets are not exactly what I expect. Put char is 348. Put s is 3d2. Like if I put a breakpoint like anywhere here, it should be okay. But I don't know. Do I have? I don't have an executable running right now. Yeah, but worst case, I'll do it like later. No. Oh, maybe it's. I don't remember what segment it is, to be honest. I mean, it is supposed to be what I mentioned. So, okay, it's always on top of it. Okay. I guess I need a break. But let's clear the breakpoint. Let's do target remote. And here I wanted to also do QEMU i386, to be honest. This was the preparation for ARM. This is something else. I did the right thing, actually. Yeah, so now it's getting like long and boring, and I actually need to go myself. But, no. Oh, there you are. Touch. Not really connected. Okay. Now I forgot the addresses. Let's see. Like if I had like the infinite loop and I and I'll like would put like Control C in any place where I have the infinite loop, I would be able like to jump to, I'd be able like to, I would be able like to stop, like there would be high probability that I will have like put S or put X or something like that in this procedure. This is actually like how I like to use like addresses usually in things that like I'm not sure like exactly what is going on. But this is like the setup code, and an int call will not be a bad idea. So let's have a look at this. And BIOS call is definitely something that I'm interested in. All right, so let's do the int. Oh. 2E9. Oops, this was bad. And I'm going to do it here. Oh, so I probably put a wrong address. Okay, so here, look what's happening. Like, so here I'm like in the function 2E9, and if I compare it to what I have in this side, in the right-hand side, then it looks pretty much the same. Like ALESI, 03AL, I move this address here, I push registers, and I called interrupt here. Okay, so if I go ahead, and I'm not sure right now which interrupt call it is, right? But what I am sure is that even though I'm doing like this single stepping here, then unfortunately, it doesn't really work because the QEMU and GDB combination here is bogus. So I need to like delete the breakpoint, and only then like I'll be able like to hopefully I'll be able like to proceed. And so, and for breakpoint, I need to clear like all of them, and then I will proceed. It's a stupid bug, okay? But here we have like something that is likely to be like with a string. Let's see what is like the loop counter. That's ECX. What is its value? So it's 6. So I can go ahead and step 6 times, and then I'll be past it, and then I pop from the stack, and I can see like the registers, and so on. And like these particular things will probably not do too much, but we have this guy, okay? Like this little arrow here. After like the booting from ROM, that is booting from ROM is not mine, it's from the bootloader. So somebody called int call, okay? And I saw this character. And where did I saw this character? When I actually went and called from the assembly function, and let's have a look at this. Sorry. Actually, maybe I called it from main. I don't even remember anymore. No, so it was from header.s. Yeah. So somebody called run hello header, and I called put s here, right? So put s, as we saw before, although there are several versions of it, it calls its nice friend put char, right? So let's see what put s does. Put s calls some other function that was put char actually. And if we look at like put char, then put char calls another function, like at address t2 is 7, that's die plus something. And it also calls init regs, and it also calls int call, okay? That's what it does like here. So let's see where we were after this. So we have this particular case. Look at like the instruction. This is under the C segment. And from experience, I can tell you that here we are going to do like, this is the interrupt handling itself, okay? So there's going to be this, and I cannot just fini. And then we're going to return pushing like two things. And after that, sometime we're going to have iret, and then we'll get back to wherever like we seek. But these things are not necessarily so like easy or like nice for us. Let's put it this way. Okay. So let's go ahead, and I removed all the breakpoint. I remind you, and see where put char is. So put char is 348. So 348 was put char. Actually, this I know what is the problem. The address has changed in what I was looking at earlier. So there is also put s. So let's see 348. I mean, if I just go and step this instruction enough, like let's say that I do NE, I don't know, 1000, then okay, here we have more prints, right? So let's see where I got stuck again in the C segment. If I do again the step instructions, then here I look, here I'm in some other place, like 119113. I'm not prefixed by C. So this is like how I do. I go like back and forth between it. So let's see if I have 1913, what it is. And apparently it's in init regs, right? Now, init regs, it has like a simple return. So I will just go until the return. So let's go one, pound. I need to get rid of the breakpoint because of debugging QEMU. Sorry, it's delete. Clear is in KDB. And okay, so now I am in a repeat statement. So I need to just go through it. And I know what inforex does, so I'm not too worried about it. Move. And then ret. And now we are in 36E. Now, 36E is right after call init regs, okay? And after looping put char. So there it is. I'm in put char, right? So I can go ahead, I prepare the registers, and sooner or later I'm going to do like another call. So let's go and see where is the jump. And we jump to 2E9. Okay, like before we were here, there is call to 2E7, and we already saw 2E7 or 2E9. Like this was how it was, right? Hold on. 2E9. So yeah, so this is it. Okay. like what we see here is not exactly representing the reality. See, one of like the annoying things when you try like to only reverse engineer it with a bogus thing. So look what we have here. Like we have these bad instructions, we have this, we have that. But this is the real thing. We came to 2 in 9, which is the int call. So if we do this int call, we will see another things. And in every such print, by the way, like there is a moving of the cursor, and then there is like putting off the putting itself. So I'll go until. So here we have repeat. So let's see how long is the repeat. Let's see what is the value of ECX. 6. We'll skip that. Boom, 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 boom. Int 10. Boom. And now we have like something on the screen. Okay. So these are like some ways to debug. It's a good idea to know like the real addresses. Okay. So now I'm going to clear here. To delete, I'm going to h break on, not on int call, now on put s, read d2, and I already assume like from the other one that they're going to be prefixed with 10. Okay. Read d2, and there is a chance that nobody calls it. Yeah, of course. Maybe people call only put char or something like that. But I'm going to break here. And I'm going to continue. And this time I got it right. To be honest, I am not sure what. I probably missed some character, like I had a typo at the first time. I did want to take the long path of showing you like a lot of next instruction and how, and I didn't even do it. The long path would not be calling 100,000 instruction or doing Control C, okay? But look what happened. Like we did a breakpoint and there like we have welcome to Ron's demonstration, boot blah, 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 says hi. And let's see what we have here. So here we have push bx and this guy here. And look at the code here. This is something that we have like the move this guy to AX. We have, and then we have call to put S and we have call to int call. So when, let's see who called us and what we have like in the memory right now. So I look like in the registers and I see that data segment is 1000. Okay. And I see EAX that this is the address. If I look like at the address, okay, let's like this of EAX, a lot of nulls. If I look at the address of data segment times 16 plus EAX, I see something that looks like text actually. If I go ahead and just print it as a string, then look what's going on. The next caller is this put s round 0, and then after it, like in memory, we have this string and we have this and we have that. Okay. So what I could actually do is also like search in memory, like for the strings that I already know that exist. So what I can actually do is like look in memory for the strings that I already know that exist, and you know, find my way like around. But this is like the argument is this guy. All right. This is like the argument, and let's just see where we were. If we look at it like this, then okay, we start by pushing px. And one of the annoying things in real mode is that a lot of time, and like it's true, many times you're going to see some code, and if like you step instruction, you're going to see another code because it's bug like in how GDB interprets it. So you need to have like nerves of steel to cope with some of these annoying things. Okay. So like I push it, now I move like AX to, whoa. I didn't do anything because of the bug in GDB that doesn't allow me to single step or step if I have breakpoints. So look how not nice it is, okay? Like people jump over window for less than that, from window over less than that. So okay, so I do the push here. I move AX to BAX. By the way, if you like Intel syntax more, then you can go and do set this assembly flavor Intel, and then you will see things that look like this. Okay, so look at this. Like we're going to move AX bytes, and look what we have. Like here we see BP, and before what did we push? We saw BX. So here and like in obj dump that we saw earlier, we see something that like is not really with us. Okay, so let's see what is BP. It's 0. And what is BX? What we actually care about. Trust me, if like these things can make you want to kill yourself. Like if you never encountered it and like trust the debugger or trust OptDump, I mean, they're just doing sometimes bad work with the disassembly, especially in real mode and especially in some ARM modes. So you need to go ahead and look like what the opcodes really mean, okay? So this can be really, really, really frustrating. So this is like a lie. Like this line is a lie. It's not BP. Otherwise, what we would have here, and let's single step until the call. So here we have call to 346. That is, I think, put char. Yeah. So it's 348 and it's put char. Okay. So that's what we have here. And like, by the way, one of the reasons for these things is simply real mode. Okay. Like some things will not align exactly the way you expect it. Like you expect 4 bytes like of addresses, but it's 2 bytes and so on and so forth. Like these things are annoying. Okay. But here we have a call to put char, and the call to put char actually wants to put something like in AL here. Okay. So obviously I'm not calling it with the wrong registers because EAX now is 52. Okay. So 52, if you look like at ASCII, then 52 would be, let's see, 52, 52, 52. R, right? From like the RON print that I showed in memory, right? So this is something that I see. However, how in the world did it get into EAX if the disassembler told me that I move from this guy, from like EBP? What was it? Let's see, before the disassembler said that I move into AX, right? From EBP plus DI. And EBP index is 0, or what I actually, so it's like, it's just not it. Like what I really wanted is to move from BX, not from BP, okay? So what interested me is not to see what is the memory, let's say X slash, just for fun, 4C, okay? At DS in real mode, it's important, times 16 plus BP plus DI, all zeros. But if it was BX, okay, what did I miss here? Hold on. Okay, maybe I resetted them. So this was AX. Yeah, so EBP is 0 and BX is this guy. So it was set to something else at the meantime. It wasn't the bad. It wasn't the best. I should have shown it like before, okay? Because we like increase BX and we do all kind of things. Let's see. We move to AX because I changed like the disassembly flavor, and you know what, let's just have a look at the original function. That, okay, so we pushed bx, we moved something to ax, we moved ax to bx. This was the parameter that like we had at the beginning, okay? And then we moved bx in this to this, and then I actually don't think we didn't jump, I believe. We increased bx. Okay. So anyway, that was, I got a little tired, like, let's see. So it's supposed to be ds, that is segment plus 16, plus this bx guy. Yeah, oh, so di changed since then. And probably it wasn't di, probably was e. Yeah, it was di. Okay. It's not really important. If I go to this breakpoint again, then I'll be able like to check it again. I didn't see like the code. So, but the important thing here is that like this assembler was also wrong, and like here I already increased like ebx. Okay, so it points like to the next iteration. So instead of run, then it's like on and so on. So this is another thing that I want like to illustrate. But now, if you know more or less where the functions are, and you can understand the calling conventions, then you can find your way around it. So to wrap it up, because it's been a long session, and now I can tell you that nobody's going to watch it because it's like 3 hours of like talk, right? So to wrap it up, like what we did today, like so this is how you can convince yourself of some things, how you can like learn about like the early debugging things, and later on in the process you can go and like put like a breakpoint in start kernel, and this is a completely different address space in protected mode. We can see it very well because like it's much longer also, and then like you can do go continue, sorry, and I will just select whatever, and like in this particular case I should have put a hardware breakpoint actually. So these are like the kind of challenges like you can meet, okay? And I hope that this makes it clear more or less. To wrap it up, like especially if you do it, you know, like live, there are always going to be things, especially if it's like so long. And but like to wrap it up, like what we did today was at the end also debugging and proving and showing like how these things go. But in addition to it, we looked a bit at the boot code of x86, and we convinced ourselves that when we call the kernel start kernel, then it actually happens from architecture dependent code that is being crafted in a very particular way, in a very well-known way, using the header that is well-known. I showed you how to debug some things that come from the header itself, and how some BIOS functions are potentially implemented, and so on. And like I showed quite a lot of things, and I can guarantee you that you know, at least for the first time, figuring out some of them can take hours, days, weeks, months, forever. So I hope that it was a little bit interesting. And for the next time, I'd be happy like to accept feedback when to do it. Maybe I'll do it next week, and for sure I'll make it shorter. And for the next time, I'm going to either proceed showing some more things on this domain, and or go and show the equivalents in ARM and kind of like the debugging and stuff like that. Now, if we went back to, let's do the run KVM script. Okay, here I need to recompile like with serial. And this is what happens when you do things for too long. So let's do it without the serial. Let's do what I got earlier. Yeah, so I hope you can see it. I'll just do whatever. So one of the other things that I want to show is, as I mentioned, the population of the root file system, what it does, and what is the device model in Linux. So, oops, it's dev. So, okay, it's not mounted probably. Yeah, because I didn't run the init. I know. There is no command line. Yeah, I probably didn't even provide init for this one. So, but if I did s-dash.s, there's no sysdev. What I need to do? To be honest, I am not even sure what I'm running right now. But I can go and mount ht sys or sysfs and non sys. Okay, it's not even worth the debugging of it right now. Okay, but I'll figure out what is being run here, and although it is quite annoying for me. But that's what I did, right? It's because I need to first mount proc. Could it be? Although no such device. Of course, there will not be PS. It will respawn. I actually think that this one maybe even doesn't support execution of shell script, like this particular kernel that was rebuilt. But it doesn't matter so much. Anyway, next time I will either cover ARM or cover a little bit of the device model, or proceed with this one, or proceed with some more debugging tricks. And I'm happy to receive things like suggestions. And wow, those of you who stayed and actually survived, it's really, really, really impressive. So I think it's time to go and do some other things. And it was dynamic. I hope it was worth your time.
Yeah, this was great. Yeah, I thought it was really interesting. It would definitely be cool to see how a driver works or something like that, maybe in the future, or how you'd go about debugging a driver.
Yeah, so we'll need to set up an example of that, and can do it definitely. But
Awesome.
I mean, there are a lot of things, and I use my sessions as a placeholder for other people to show their stuff. I hope we'll get more lectures to the meetup, and that everything will be okay. All right. Now,
Yeah.
I will upload it probably to YouTube.
Yes.
So I'm not an expert on, I don't know, my channel, my
please.
videos.
Yeah. That'd be really
Channel.
useful if you could, because there's a lot there. So it's nice to be able
There
to
is a lot, wow, but it was so long and not the bestly organized. So this was like the previous meetup. It was also
Yeah.
like pretty long, and
Yep.
I showed all kind of things. Hopefully some shorter. I will not edit this video, but like I add things like there is a playlist. I put it like this, and I will add things that are interesting to the playlist. Maybe. I mean, I'm not a social marketer, and I also have some other things to do. Yeah. So anyway, thanks for everybody who joined.
Thanks a lot.
And who survived. Like, it's very appreciated. Not
Yeah.
trivial.
Thanks a lot, Ron.
Sure. And I'm going to stop now. And if you want to just talk, I stop the recording. If you want to talk a couple of minutes, then let me know. Like, I'm still here. Let's stop this. How do we stop it? Oh,
Yeah. Stop
yeah.
recording.
Stop recording, stop streaming, which didn't work anyway. Yeah. So, okay. So I will hopefully cut like the end of it anyway, but that's the end of the recording, and see you in the next meetup session, whatever, which will be, I think, next week, maybe next Sunday.
Okay.
Yeah, that'd be
And
cool.
I'd be happy if you guys submitted like talks and so on, but stop recording.
Okay.
Yeah.